Okay, let's get started. How's everybody doing? Good. Everyone ready for the snow day in Jacksonville? Right. Everyone and seen their moms posting it on Facebook and stuff. It's a big news. If there is snow, I will cancel class next Thursday for an official snow day, just so I could say that. I don't know. I don't think anybody knows what to do. They do? Okay, well, cool. No, I bet it's going to be just like slush and for like, you know, enough for, yeah, right. It'll be an excuse. I don't, it changes every day. I shouldn't have said anything. It's all fake. No, it's going to be 70 degrees probably outside. All right. Who knows what we're doing today? What did I say on Tuesday? Math. Yeah, we're actually going to write like numbers and stuff instead of just concepts. So today is going to be the first. Am I blocking it? I'll scoot back a little bit. Today's going to be the first lecture on like this next series. We're introducing a really, really important topic. So this is going to be the bulk of your exam one, basically, and it's soil composition in the terms of what we call a phase diagram. And we'll get through this and we'll go through all the background here in a little bit. And basically what sets soil apart is the fact that it is composed of a bunch of different stuff. So like, it's not like steel and it's not like concrete where it's like, you know, it looks like a single mass of material that we can then like calculate the strength of or have a homogeneous strength. Like if you took a scoop of soil and you zoomed in and looked at it, like you would see it's different granule material, it's different amounts of water, there's void space, the distribution is all over the place. So all we have to do is define some of these physical characteristics with these key indices. And I'll go over this in a second, but basically it's all this volume and density relationships. Who remembers what density is? Mass over volume. Yeah. Did you guys go to elementary school and do this little triangle thing? The DMV, density equals mass divided by volume. So if you need to calculate volume, you put your thumb over volume and it's mass divided by density. This helped me pass the 5th grade. So I don't know about you guys, but we will be using this a lot. So like basically in this class, keeping track of the units, knowing that, okay, density is pounds over a volume. So if I need to calculate density, then I look for something that has pounds and I look for something that has volume and then I can calculate it that way. You know, looking at it both ways, use the units to help you solve an equation if you can't remember it in your mind. So this is going to be the fundamental equation that is then applied to a different aspects of soil engineering here. Okay, so these are all the same as last time. So next week we will start our lab groups. So please check those and just know like the first, when you sit down, I'll ask you guys to sit in your lab group. So kind of get a sense of where everything is. Your quiz number 1 is going to be posted today. I have it set to publish at 4 p.m. So right after class, you should be able to view it. It's like 6-8 questions. I can't even remember. It's all like based off of what we're learning today and what we learned on Tuesday. So like if you have the time, what I would recommend is just like stick around someplace, go sit in a hammock and just knock it out right now so you don't have to worry about it tomorrow because it will be due tomorrow at midnight. For those of you who went to last night's meeting for ASCE, the student symposium meeting, super cool. I hope it was informal or information or whatever, you got what you need out of it. I just want to plug this again. So next Wednesday, if you do intend to go to the ASCE like student conference, then this is a mandatory meeting. So we're not like in the information stage anymore. We're like, hey, you have to show up on this and actually sign some forms. So that'll be next Wednesday, 6 to 7 p.m. on the 4th floor. So room 4. Again, if you know people in ASCE, just ask them or follow their social media. They'll post it on there too, but at least wanted to plug that. Just wanted to share this one more time, just for those who weren't here on Tuesday, but I have an opportunity to hire some undergraduate research assistants to help administer some of these elementary school camps. They're a lot of fun. You work with kids, you do like hands-on engineering activities. I don't know the schedule of it yet, so I know that's a big factor in it. But if you're interested at all, just send me an email and shoot me your resume so I can share it with the other professors. And please let me know by tomorrow anytime. So yeah, I know I talked to some of y'all here after class, but just like send me another email if you haven't already, just to touch base with this. Okay, so we are going to be working in the components and volumetric relationships. Volumetric meaning we're looking at mass, volume, and density of soil. So this is kind of that first fundamental thing of geotechnical engineering that we based like everything off of. So this is the first portion where we're looking to define the characteristics of soil, of the ground, and then we assign strength parameters, and then we do our analysis based off of that. But this is that first important part where without these volumetric relationships, we can't work in the mechanics space. So we can't assign the models and we can't assign the mathematical values that then allow us to predict the strength and predict the behavior. So that being said, these are the two chapters in the two textbooks, but also this is everywhere. So you can just Google whatever, density, soil, phase diagrams, it'll pop up. There's lots of study guides online. So what we talked about last week or last class was recapping kind of the variability of soil, why geology is important, because that helps us understand how the soil got to where it currently is. And now what we're going to be looking at is how do we quantify that behavior? So quantifying meaning we put numbers to it so we can put it in math equations and we can get the engineering salary that we deserve. So it all is based off of the type of weathering. So we went over physical and chemical, and then the types of transport. So some of those examples, again, were like residual soils. Who remembers what residual soil means? What was that? Yeah, leftover or not transported at all. So like it weathers and then it just stays put there. So it's usually not too far away from the parent rock that it was formed from. Who remembers what glacial means? Oh yeah, good. That was fair. Yep, yeah. Glacial eroded soils is, you'll never guess it, eroded by a glacier or a glacier if you don't live in the US. Wind is aeolian, marine is a type of like sea settled soil, and then fluvial is rivers. So a lot of times I said in Florida, we'll be dealing with a lot of fluvial, meaning it was deposited by a river, either St. John's or rivers that don't exist anymore, or marine sediment, meaning it was deposited whenever Florida was just a shallow sea or the landmass was being exposed and submerged over and over again. So we talked about the lovely psychedelic looking geologic map and the different things that we can get from that. The key things that it will tell us are, why does it always do this? The key things it'll tell us is the geologic formation. Does anyone remember the name of like one of them that I talked about? Yeah, Hawthorne group of soils. That's one. Remember any other ones? Ocala limestone. Yeah, basically you can pick like any of the random small towns in Florida and just put limestone after it. Like there's Avon Park, Miami limestone. I guess that's a big city, but you know, a lot of them are named after the cities around there. Cypress Head Formation is another one. That's the kind of the I don't even see it on here. I don't remember the color, but there's a bunch of different ones out there. And so this tells us about the formation, which just groups the soil into different categories with similar characteristics. So the characteristics might be composition, so primarily shelly or primarily full of fossils or primarily clay, as well as the deposition. So like, okay, this Hawthorne group it's all marine sediment deposited in the Miocene age. So it's just kind of good for that. So formation and composition, as well as the geologic age. So what are some of the things, though, that geology maps or rock maps or geologic maps, they cannot tell us?
Regional.
Yeah, it's site-specific. So it is good for regional. Like, okay, so Miami-Dade County consists of this and this, or Duval up there kind of has 3 primary sediments. It's good for regional. It's not good for site-specific. So I can't use this and be like, all right, the Wawa at the corner of Beach and Southside has this on it. So it's not good for site-specific. It's also not good for strength parameters. because there's no quantifying here. We can't use the mechanics. We can't develop anything on mechanics side of this. So strength is all based off of, does this amount of loading actually withstand, or can the soil actually withstand this amount of loading? We have no numbers associated with this. Yeah. So you may have used the USDA soil map. Yeah, that is different than the geologic map. Yeah, so that one's a lot more accurate, right? Like that'll show you how it changes throughout the site. Those were developed by counties and then conglomerated all together in this giant thing. So that can be good for a site specific. Geologic scale though, remember these maps are based off of like well points, these data points. So I don't know how well you can see that there, but from Pensacola to like Mayport, there's like 12 data points maybe. So like, like that's a long distance, all of I-10 right there. And it's only based off of 12 data points. So it's not as good from a finite point. So you can see, if you look at that cross section a little bit more too, you'll see some sections where they just draw these little squiggly lines and they're like, I don't know, some point between here and here, the soil changes, but we don't know exactly where. So they just draw a little squiggly line there to show it. So, it can't be as precise on that point. Okay, so the whole reason why we spend 2 weeks here, and I've already kind of mentioned this before, but if you just Google soil, or if you think about soil, or you've driven anywhere in Florida, or maybe you've gone up to Georgia or anywhere else, you'll see like soil is different all over the place. It's different color, different composition, different sizes, different uses. And so we have to spend a lot of time first defining the characteristics, like some very basic physical characteristics of the soil, where like if you were to Google steel or think about steel, you probably have a picture that comes up in your mind, right? Shiny metal. Like I'm not saying steel isn't important to study, but it's basically not important to study it. No, there's just not as much diversity when it comes to steel. Yes, there's different grades, there's different types of strengths and different like ductility and everything, but steel is something that we make as humans, so we get a chance to like have say in the input. Soil is something that we have to define ourselves. Like we don't get a chance to really make the soil or choose the soil on site. Same with concrete too. Concrete, there's obviously more variability than steel just based off of the mixtures and all this stuff that Dr. Islam talked about, hopefully last semester. But still with soil, the diversity and the variability is much, much greater. So if we were to just zoom in to soil, what we are going to say is we are going to simplify it based off of two things. There is going to be a portion of it that is solid, and there's going to be a portion of it that is nothing or void. It's going to have void space in between it. And so we first start by defining these two things. There's a solid portion, there is a void portion. Now, obviously in your mind, hopefully just by looking at this picture, you can think like, well, the solid portion could be made up of a bunch of different stuff. Like it could be made up of granite, or it could be made up of a quartz, or it could be made up of shell. It can also be a bunch of different size material too, like you can see in the picture there, like different sizes of material. But for now, we're just going to say, all right, we have a solid portion, we have a void portion. That void portion can also be made up of different things too. It can be made up of water. And that water could be fresh water, it could be salt water, it could be toxic water, I don't know, it could be a bunch of other like types of liquid. But it's also going to be made up of air too. There's going to be air voids trapped within that void section too. And that air though could be fresh air, whatever, nitrogen, oxygen, whatever the heck we're breathing. But it could also be like gas, like methane or petroleum or other things too. So we can get really into the weeds of defining how that's going to change the behavior of the soil. But for now, what we're caring about is three phases: a solid, and then the void is going to be air and water. Yeah. So
Any kind of answer that there's going to be different types of like water, seawater, water, whatever. Basically, that's the way that the soil is going to interact with each other, like the solids are going to interact with each other.
Yeah, it definitely can. Yeah. I mean, if we think about like soil failing because the particles will like move past each other, you know, like kind of shear, like move past each other. Like if it is a less viscous material or a more viscous material, that could change it. And then also the geohazard, that video of the quick clay. Remember, I was saying that was from water that used to be salt water and now is fresh water. So that salt water changed the electrochemistry. So yes, it can. So what we do is what we as soil engineers and as geotechs, the first thing that we usually define are these things called a three-phase diagram. So we're taking something that looks complex like this, like where we have solid portion, air portion, and water portion, but then we're summarizing it into these three categories of air, water, and solid. Now, in order for us to use this soil phase diagram shown there on the bottom right, and we're going to go through all of these parameters and what they mean and how to calculate them. But in order for us to use them, we have to assume a certain things. First of all, that the mass of air is just normal air that has a mass of 0. So it's not any like thing special. It's not helium. It's not like some like really dense methane or anything. Like we're just dealing with regular air, and the mass is going to be assumed to be 0 of air. This is again why we're engineers and not scientists, and why if you have any friends in the sciences, they probably get mad at you every time you say I'm a scientist, because we make these assumptions that the scientists don't necessarily care about. The other thing is that we are dealing with a homogeneous material. Homogeneous material, which means it's all the same thing. So we know for a fact that's not true, right? If you take a scoop of soil, you could see like some of the little grains are see-through, some of them are not. Like they're all made of different materials. But what we care about as engineers is the average of those solids. So from here on out, we're going to be assuming like and calculating properties based off of this solid portion. And really what we're doing is assuming the average value. And this will be illustrated a little bit better in the labs whenever you actually see the soil hands-on and get a chance to look at it. The value that we're using to quantify that is technically the average. So we're just assuming it's a homogeneous material. The other thing that we're assuming too is that the solid portion is non-absorbent. So this makes our life a little bit easier. You guys remember in concrete and in CE materials last year, we had when we were dealing with like the water cement ratios of sand or of concrete, you had to account for the absorption. You remember what absorption is from aggregate? Can anyone tell me? Does anyone remember that well? It's the moisture content at the saturated surface dry state. So essentially it's the moisture content at which the aggregate is happy and won't absorb water and won't release water to our concrete mix. So that's really nice. So this is kind of nice because in soil, we're just assuming that all of these little tiny grains are non-absorbent. So we don't have to deal with like, if we add water to the soil, it's going to like fall into the pore space at all. It's small enough that we're assuming it's non-absorbent. So once we have that, then what we can do is use these phase diagrams as shown here to calculate the volumetric portions on the left and then the mass portions on the right. Now, remember, what was that little triangle thing, Illuminati thing I showed at the beginning? How can we calculate mass if we have volume or volume if we have mass? What's the thing that translates in between here? Density. Yeah. So that's going to be the thing that we use to help us translate between these. Now, once we define it, I'm starting from the basics. What you'll see is like from here on out in the next few slides, based off of all of these values here, so volume total, volume solid, volume water, volume voids, mass water, mass solid, mass total. Based off of these, we develop certain ratios and certain values that help us define the physical relationship of the soil. That sounds weird. The physical relationship, the physical parameters of the soil. And why we want to help us define it using numbers is, again, so we can use the quantifying, like, so we can use that in mechanics in the future. So in engineering practice and in the lab, usually what we can do, we can measure the total volume of soil, right? How much of it is in a dump truck? Like we can measure the volume. How much of the soil are we pouring into a like a mold or a beaker? Or how much soil are we excavating from the site to build our roadway? You know, we can measure the total volume of soil. We can usually measure the mass of water pretty easily, and we'll talk about how we do that. But hopefully you're remembering from your CE materials class how you can measure mass of water using an oven, let's just say. And then we can also measure the mass of dry solids pretty easily. So these are usually the go-to things to do, but throughout this class, and especially in the lab section, we'll look at other ways and other easy tests that will help us fill out the entire phase diagram. And once we have all of these values known, then we can easily calculate these indices and these quantifiable, like defining characteristic numbers that then we use for the design side of things. So that's kind of big picture there. So density, if you haven't memorized that, I mean, you should because you're a college student in engineering school, but please like just know like the density relationship, how to find those, how to switch this around to calculate volume and mass and so on and so forth is important. So why we care about density too, as well as I said previously, soil will fail through a shearing behavior, meaning what is causing soil most likely to fail is the particles rolling over each other and moving and separating and shearing. So what that means is that soil fails through a frictional process. And you guys all took like physics, again, because you're in this classroom. So if you remember from physics, the friction force or whatever friction is equal to this frictional coefficient, which is a material property, times what? Yeah, I don't know. I mean, that's the spring thing, but it's times n, which is the normal force, right? So the more force that we have acting on something, the harder or the stronger that friction resistance is, right? And we've all thought about that, like that's how air hockey works. We have air blowing up against the puck, so there's little friction. If you have a thing of sandpaper and you push really hard on it, then it's hard to pull it, shear it sideways because you're increasing that normal force. So same with soil. As we increase the density or as we increase that normal force of soil, we will increase the strength. So usually we'd see almost like a linear relationship here where the increase of density, so the more dense our soil is, the stronger it is against shearing. So let me just put that. So against shearing. So this is why density is one of the most important things to define in soil, and why a lot of our index parameters, especially one that we'll talk about right in this next slide, is basically a way of easily or quickly defining the density of soil. Because the one issue about density, or not the issue, but the one area that can be kind of confusing is the units, right? Like we're in mass divided by volume. So like grams per cubic centimeter. That might be difficult to scale up on a construction site level, right? Like talking about grams per cubic centimeter. Yeah, we can do the like the conversions and everything. But what we always aim to do is look at like unitless values of something to find this behavior. So what we look to develop all based off of this is important, like I'm just going to call them like ratios, or what are they're really called indices or indexing indices. Like it's essentially scales that are developed from the phase diagram for strength estimation and geotechnical design. So it's kind of like, think about like hurricane like scales or something, like we can all think of a category 5 storm and what that means and the things associated with it. Like they could easily just say like, oh, like this storm has a max wind of 190 miles per hour or whatever it is. But they use these scales or this like index instead to more easily communicate things across. So same thing in soil. Like, yes, we could just talk about density the entire time, or we could just talk about the strength the entire time, but it helps us in communication and in design when we deal with these unitless indices instead. So some of them that we'll talk about are these ratios. They allow us also, as I said before, they scale from the investigation, so the lab setting, to the field setting. So we're doing our trial error in the lab. We find the value that we want or the mix of whatever design that we want in the lab, and then we can scale this up into our site scale. So some of these are the void ratio, which we'll talk about here in a little bit. This is one of the most important ones in geotechnical engineering, and especially in the mechanics of soil, because it is directly correlated to the density of soil and the compaction of soil, like anything that we could be doing to change the density of soil. Some of the other ones, porosity, degree of saturation, which you may have touched on a little bit in your CE materials class for organic or for aggregate, water or moisture content. Hopefully everyone is already familiar with that one from your CE materials class, but we're going to review it again and do this for in terms of soil. The unit weights, which is just a engineering way of showing density. So we aren't using units like slugs or grams or anything. We're using force per cubic area, or cubic length. So force per volume. Specific gravity. Do you guys remember what that one is from CE materials? What is specific gravity? Yes, it's the density divided by the density of water. So it's just a unitless way of talking about what the density of that material is. Now, if you remember, like in the CE materials class, aggregate was hard to define, right? Because we had like the specific gravity of absorption and saturated surface dry and apparent and bulk and all that stuff. You guys remember that lab? That was probably a horrible experience. Well, luckily, do that first assumption of our solid portion not absorbing anything, we're only gonna have to deal with one specific gravity in this class, which is just the specific gravity of solids. So that's a very nice thing, hopefully. But we have other terms like relative density. All of these are probably just like words to you right now, but hopefully by the end of this class, you'll be able to, one, hear these words, think of the equation that allows us to calculate these terms, and then also think about what that relates to in the grander scheme of like geotechnical design. So like that's kind of the goal of this here. All right, let's talk about the most important one, our void ratio. Okay, so the void ratio is calculated in this crazy hard equation. Just give me a little bit to write it down real quick. Oh, my hand cramps just writing all that out. Yeah, no, it's very basic. It's the volume of voids divided by the volume of solid portion in our phase diagram. So again, thinking back, the first step is to use density relationships, use some of the values that are given to us or the values that we can find in the lab to first fill this out. So we know the weight of the solid, we know the volume of the solid, we know the weight, the volume of water in the air and all that thing. And then we can fill out these values here. So the void ratio is the volume of voids divided by the volume of solid. Now, the tricky part, for whatever reason, we use E, the variable E, to represent void ratio. I wish I had like some cool story of why we do that. I have no idea why, but E is the representative of the void ratio. So if we're talking about just equation wise, it's volume of void divided by the volume of solid. Now I'm going to tell you something and like, turn your brain not in like, oh, like don't get it confused. I'm going to tell you something that is a lot of people will confuse us with. It is not volume of voids divided by total volume. That's one of the things I see like most mistake wise. It's these two separate things. So volume of voids divided by the volume of solids. So the two separate things. It's not, and the way that you can kind of hopefully help remember it is just expressed as a decimal. So it's not in a percentage form at all. So thinking about density, like remember I said this relates to density. Density is mass divided by volume. So if we have something with a really, really high density, what do you think would be the void ratio? Would the void ratio be really high or very low? It'd be very low. So if we have something with a high density, so the sample of soil with a very high density, mass divided by volume, high number, do you think the void ratio will be high or low? Yeah, it'll be low. Oh, you guys are much smarter than last time I thought this. Yeah, think about the equation. So if it's a really large number, that means we have a much higher significant volume of voids than we have volume of solid. And I mean, we already said the volume of void, yes, there's water in it, but there's also air, and air has no mass at all. So like solid portion is always going to be heavier or have a more mass than the void portion. So the tricky thing is since it's these two separate values, so volume of void and volume of solid, the ranges aren't really like intuitive. Like usually like it's going to be related to the density. But like what we see is like anywhere between like 0.3 to like a value of 2. So it's kind of hard. But like just keep in your mind like 0.2 or 0.1 to 2. You'd rarely see a number greater than 2 unless it's very, very loose material, very, very like soft or low density material. So yeah, as the void ratio decreases, the density will increase or vice versa. So there are transverse values there. So the other one that this often gets confused with, and I'm going to show it right back to back just so you can kind of show, that is the porosity. So the porosity is the volume of voids, but instead of just comparing it to the solid portion, we look at the total volume. I guess I should just put total volume instead of volume total. It's a weird way of saying it. But this is the volume of voids here divided by the total volume. If it helps, like on each page, circle the ones that it involves on the phase diagram. So this one is shown. Does anybody know the letter that's associated with it?
P.
P. Oh, close. That area of the alphabet. No, we're still sticking in English alphabet, but it's N. No idea why. Again, but N. I should probably make up a cool saying about it or something, just so this isn't as boring. But yeah, so it's N and it's volume of voids divided by the total volume. But this one, because we're dividing something that is a part of the larger thing, so like the volume of voids can never be greater than the total volume, right? So for this one, we express it as a percentage. So we show it in percentage form just to help us remember the equation a little bit easier. So it's expressed as a percentage, which hopefully will help us remember it, because if we have a porosity of 0, that means we have what? What was that? We just have a solid chunk of something, right? There's no voids in it. If we have a porosity of 100%, that means we just have, we just got this, right? So like you can kind of visualize the two extremes here. So generally a more dense material will be a higher or a lower porosity. And generally a less dense material will be a higher porosity because there's more pore space. It's kind of that way. So it's always shown between 0 and 100%. And one of the cool things is that these void ratio and porosity is closely related here. And I'm just going to go through this really quick just so I can draw on my iPad. But if we know the volume of voids, plus total volume, this, and we know the volume of voids, the total volume is volume of voids plus that volume of solid portion. If we rearrange this equation, then we have 1 over the porosity is equal to the volume of voids plus the volume of solid divided by the volume of voids. And then just the way math works, we can factor out a volume of void, where we have volume of void over volume of void plus volume of solid divided by volume of void. And if you remember what void ratio is, this is 1 over E, or 1 over the void ratio. So all this to say is we can relate this porosity value, 1 over the porosity over 1 plus 1 over E, into this handy equation here. Oh, sorry, that's not an N, that's an E. EU. So these are related to each other, and we might be able to calculate the porosity and then estimate the void ratio based off of that. So just like based off of like even the names of it, like I'd mentioned, the void ratio is used a lot in like strength estimation and strength correlation. Porosity basically says the same thing, right? It's a value that like involves the same things. But where might we use porosity, or in what industry or in what like analysis would porosity be used over void ratio if they say the same thing? What do you think? I just asked this because I'm thirsty and I want to drink water.
If you're doing drainage stuff, you want to have the porous,
Yeah, definitely. That's one of them. Like drainage in general, permeability. Like this is more so used in the modeling side of things when it comes to like aquifers, like the porosity. We have micro and macro porosity of soil sometimes. So this is used more so in the water space, where void ratio is more so used in like the structural, like compressibility, like how strong is the soil. And it's all because like in this case we care about the ability for water to flow through it. So this ratio is a better representation than the volume of voids compared to just the solid portion, or usually that's looking more so at strength. Okay, so the void ratio and the porosity, again, they are common. They kind of have the same goal, but different ways of calculating. And if you need to remember, like the decimal should help you kind of remember this equation where it's just these two independent things. So the next one is degree of saturation. I don't know if you guys covered this in CE materials or not, but it's pretty straightforward. The degree of saturation is another volumetric equation. We're looking at the volume of water, but we're dividing it by the volume of void. So what letter this uses? Yes, it is an S. We finally have one that makes sense. Should get the Wheel of Fortune soundtrack there. Yeah, so we have an S. It's volume of void divided by the volume of water divided by the volume of voids. And this one we also show in percentage form, because the volume of water is never going to exceed the volume of voids. Now in CE materials, it could, because you can have that free moisture on the surface, if you remember that. But in our simplified geotech minds, it's never going to exceed that. So this volume of water is never going to be greater than the vessel that it's able to be held in. So volume of water, volume of voids. Essentially tells us what percentage of our volume of voids is filled with water. That's what the degree of saturation is telling us. So again, shown as a percentage, which makes our life easier. And I should say, again, we're always expressing them or showing them as a percentage, but just like percentages, anytime you're doing the calculations, then you have to put it back in decimal form. You know, like you're presenting it in percentage form, but then in equations that incorporate degree of saturation or whatever, then you put it back in decimal to do the calculation part. So the maximum possible values here are, of course, 0 and 100%. And we see these maximum ranges pretty often. 0 degree of saturation means the soil is what? Yeah, it's just bone dry. We just took it out of the oven with our gloves and glasses on, hopefully. And 100% degree of saturation means it's fully saturated. Yeah, not just wet, but fully saturated, which means there is 0 air in it. So oven dry is 0. When saturated is 100%. But we will see in this case, this is an important case that helps us simplify a lot of things because that volume of air in this case is going to be 0. So there's no volume of air in this, which means soil is only composed of 2 things. It's only composed of water and of solid. So that helps the calculations. You know, we're taking 33% of the brain work out of it. So this is a very helpful thing. And in subsurface investigations, usually this is why we care so much about where that groundwater table is. Because the assumption is once the soil is under the groundwater table, then it's fully saturated. So that's why defining the groundwater table is important. Because above it, our degree of saturation is unknown. But below it, we assume that degree of saturation is 100%, which I'm not going to try to scare you guys away because of all the mechanics and equations and stuff, but like that makes our lives so much easier. And just because water is incompressible, you remember that Poisson's ratio kind of thing that we talked about? It's like a water balloon, like you push it in one direction, it's going to expand equally in the other direction. And since water is incompressible, and the solid portion is assumed to be incompressible, that helps our math equations so much when we're trying to estimate how the soil is going to react under loading. So saturated soil mechanics is a lot easier than this scary topic called like unsaturated soil mechanics, where if you ever want to get really deep into it and do like a PhD in soil mechanics, unsaturated soil mechanics, you could just learn for years about it because it's very hard to define the mechanics of that. Okay. One here, one of our all-time favorites that hopefully everybody's are familiar with, the water content or the moisture content. Raise your hand if you guys did this. Okay, so yeah, no, only 3 people raised their hand. All right, thank you all for raising your hand. Yeah, so this one is shown by a fancy little W sometimes. Sometimes we show it as a W.C in all uppercase, that's yelling at us. Sometimes we show it as an M.C. But the equation is the weight of the water divided by the weight of the solid portion, or the mass of the water divided by the mass of the solid portion. Either one, you know, as long as those 2 units cancel out. How do we express this number though? We show it as a freaking percentage. It was all nice and easy from here on out. Like, oh, it makes sense. Like, you know, percentage is like a 0 to 100% because like whatever, like this is percent full. But nope, they were like, this is a little bit too easy, this geotech stuff. So what we should do is just express this as a percentage. That doesn't make any sense. It's a barfing emoji. So the maximum range is technically between 0 and infinity%, which is just stupid, but it is what it is. A 0, it makes sense, right? Physically, a 0 moisture content means what? Yeah, there's 0 moisture, which means we just took it out of the oven or we just put it outside in Florida for 10 minutes. Like it's all the water has been burned off. All we have is a solid portion, only have a weight of a solid portion. But of course, the other way around of that, if our solid portion is really, really, really small or really, really light and our water is there, then like, I mean, we have a number over 0 or really small number. And what does that do to, like, if you remember from algebra, you have that asymptote thing where you can't define it, right? It's undefined. So it technically can go to infinity. Now, yeah, the issue with this in soil, where in your CE materials class, you probably didn't experience this, but in soil, it can be, and it often is greater than 100%. So most natural soil, like if you were just to go to the beach, like Atlantic Beach, and take a scoop of sand, or go out in the whatever hammocks and take a scoop of sand, most natural soil is going to be somewhere between like, oh, sorry. Well, it's in most natural soil is going to be less than 100% ish. Usually for sand, what we'd see is somewhere between like 10 to 50%. And then for reasons why we'll talk about later, the clay portion, like if we have a clay soil, usually it can be like 10 to like 90% or sometimes higher. Now you probably get where I'm going here, but if we have any organics mixed into our soil, we can have really, really high moisture contents. And hopefully it's making sense if you look at the equation why we have that, right? Like organics are made out of what type of material? Yeah, wood, trees, dead stuff that used to be filled with water. And it's also usually in Florida, organics are associated with water, right? Like they're in the bottom of lakes or an old riverbed or something. So organic soils are going to have a lot of water, but not only are they going to have a lot of water in the pore space, the solid portion is going to be super, super light because it's made out of like trees and, not minerals, not like a dense mineral. So we have a really high numerator potentially and a really small denominator potentially, which means we can have these really large values here. So organic soils, if you're lucky, you can get like 50% organics, like or whatever. But I mean, you can get it upwards of like 600% moisture contents, which is stupid to say. Like it's a percentage. It shouldn't be that high unless, so yeah, think about the equation there. Think about like what the physical meaning is, and especially whenever we start working with some of the soils and calculate these values, hopefully that'll help like add some like understanding of where these numbers are coming from. So water content, if you thought we were going to get away from that after CE materials, nope, we're in deep with the water content. All right, the density, why does that look like it's misspelled wrong? Density or unit weights. In this class, we're mainly only going to be using unit weights. So unit weights is just the density times gravity. So it's a force per volume instead of a mass times volume. And just because like that's what we're used to dealing with in loads and stresses, that's the value that we would use a lot of times. So although you still will need to know this rho number or this rho value here of mass divided by volume, in this class and hopefully in your other classes, you've been mainly focusing on gamma here, where it's the weight divided by volume. So the units that we're used to finding here would be either in like pounds per cubic foot or kilonewton per cubic meter, something along those lines. Those are the two most common ones that we would use for the unit weight or the density. Now, since we're dealing with this phase diagram, we can have various densities, very similar to the aggregates that like you studied in CE materials. So we can have just a total or natural, or what you probably are familiar with as bulk density, where that is the mass, everything that has mass or everything that has weight divided by the total volume of that. So it's just shown as this. And what's important to note is that this natural or whatever, it's the same as our bulk from our concrete. But we don't have a subscript. So anytime you see just gamma normal or rho normal or gamma normal with nothing defining underneath it, think of this equation or think of bulk, like just what it is in its current state. And then the other ones are hopefully a little like more intuitive. Like we can have the solid density, which is only the parent rock. So what is the actual grain itself? So this is only the mass of the solid portion divided by the volume of that solid portion. Obviously, we know the density of water as well, so the subscript there. So if you haven't memorized the water density of water in both forms, it will be very helpful for the FE. So another one is a gram per cubic centimeter. What is it in US units? Yeah, pounds per cubic foot. And then what is it in SI units if we were to use that? Remember, it'd be either 9.8 or 9.81 because it's just 1 times the acceleration due to gravity. Again, that's kilonewtons per cubic meter. A lot of times, and maybe on the FE handbook, I don't remember, sometimes that's just rounded up to 10 kilonewtons per cubic meter as the density of water. I don't know why we do that, but it could be there. 9,000? No, that'd be newtons per cubic meter. Yeah, 9.8. So that's the densities, but as I said before, like there's also different states of density based off of like what our soil is like in situ or in like its current state. I just used a word that I don't know if you guys heard. Have you guys heard this term in situ before? In situ. It's not institution. It's I don't know. I'm assuming it's Latin. I don't know. I've never seen it pop up on Duolingo before, so I'm assuming it's Latin. It's in situ. It basically it means in the current state or place. So this is usually defined in geotechnical or subsurface investigation as like what is it currently in the ground or as is before we excavate it up, before we build stuff on top of it, before we do anything, what is its current state? So a lot of times we'll be thinking about the in situ density and we have to think about like what is the state that it's currently in? Is it in its bulk state? Like does it have all 3 of these things? Is it in a dry state? Like is it at the surface or did something happen where like all the water's burned off? Is it in its saturated state, meaning it's under the groundwater table? And so that can affect the density mainly just because of this relationship here. So is there air in it or is there water in it? How much air and how much water? So these are some of the useful densities. Again, just to keep it consistent here, I'll just show the values. So the gamma dry is only the weight of the solid divided by the total volume. And then the saturated density is basically the mass of the water, but when the volume of air is equal to 0. So in its saturated state. Submerged density is a little hard to define, but essentially what this is, and we'll come back to this later on, but this is what we call effective density. And this is shown as a gamma either sub or sometimes gamma prime, like we see here. And all this is the saturated unit weight minus the unit weight of water. Now, don't worry too much about the submerged density. Remember this equation because it's really easy. We just take the saturated and then minus that out. But the reason why we use that is when we're calculating the stress, because soil is correlated to its strength based off of its stress, or sorry, the stress is correlated to the strength, and the saturated density and the unit weight of water, it will behave differently whenever we're talking about it being submerged or not. Because we're talking about the weight of the soil. And I'm sure you guys have experienced this before, like a weight above ground. You know, if you lift the weight and then you go in the pool, it has a different like perceived density. So that's essentially what this is. It's a perceived density in terms of the strength of it. So we'll talk more about that in a little bit. Okay, the things that help us relate to specific gravity, and this is the last one before we'll actually go through some example problems, is that specific gravity. And what's cool is like, you might remember doing the super sketchy like experiment with concrete where you just put it in a bucket, right, and measure the submerged weight, and then you take a towel and you just dry the thing. Did you guys do that in your lab last semester? Dr. Islam did that? Oh God. Okay. Well, anyways, the soil version of finding the specific gravity of solid is a lot more scientific and more engineering-y. But anyways, all it is a unitless value of density, basically. And so this is really helpful because no matter who you're talking to on the phone, whether they know the unit weight of water to be 62.4 pounds per cubic foot, or if they know the unit weight of water to be 9.81 kilonewtons per cubic meter, like if you say a specific gravity of 2.6 or 1.0 or something, like everyone's going to know what that means. So it kind of helps universe, or like, you know, helps with communication a lot. So one of the fun things we do here is, since the way our earth was made, I don't really know exactly, but most sand is going to be a quartz-based sand. Or the parent material is going to be quartz. And remember, this solid portion is, we are assuming is homogeneous, meaning it's made of the entire thing. We know realistically it's not. But since the majority of the material is going to be mostly quartz or somewhere around quartz, then usually what we look at is most sands, the specific gravity is going to have a value of 2.65. Now that might be plus or minus 0.1 or something based off of the other content in the solid portion. But you can look up, like a quartz crystal has a specific gravity of 2.65. So that means the specific gravity of most sands is going to be 2.65. And of course, that could change depending on your geologic formation. And again, the content, like if you have a lot of shell mixed into it, that might lower the specific gravity, because a shell is going to be less dense than a quartz, you know. If you're nearby like a bunch of granite rock and granite rock is like mixing into it, then that could also be a little bit higher of a value. But most ranges will be around that 2.65. So
percentage of the material for it to specific gravity?
That's a good question. I don't know if there's like a set percentage or not. What you'll see a lot in this class is it all depends on your level of risk, like the level of risk with your client or the level of project, you know. So like if you were building, again, not to pick on Wawa, but if you're building like a cookie cutter Wawa project or something that's not a significant amount of loading, you might be able to get away just assuming the size is 2.65. If you're building like a multi-million-dollar high rise that really has a lot of like risk associated with it, then you might want to do additional testing to see. But yeah, it's all kind of give or take with it. So yeah, what I want you to think of though with the specific gravity, and we'll do a lab experiment to how to calculate this. It's an easy thing for us to calculate in the lab. You can knock it out in a few hours. So it's one of those things that is a really helpful like number that allows us to define the like volumetric parameters here. But of course with this, like the things to think about is everything in relationship to water. So if our specific gravity of solid is greater than 1, then that must mean that it is more dense than water. And then specific gravity less than 1. Of course, that means it's less dense than water. So thinking about that, it's basically like how heavy the grain of soil is. And this is really important. Does anyone think what factor or what type of engineering design might this value be of really important to analyze in, especially here in Florida? Don't look in the screen if you want to guess, actually. But so this is really important when it comes to erosion protection, because we're really good at defining how particle or flow rates of water, during different events and everything. And what we see is that obviously water carries a lot of energy. And if a particle is a certain weight, then there's going to be a critical velocity of that water that's going to dislodge that particle. So this is a value, especially in Florida, when we're talking about coastal erosion or design of riprap or design of some type of artificial fill that is supposed to protect a beach, that erosion is an important value for that. And towards the end of the semester too, when we get a little bit into the design, you'll see this GS value pop up in a lot of equations when we're talking about erosion protection, because it's directly correlated to that there. Okay, so specific gravity, once we do it in the lab, it'll hopefully carry a little bit more weight to it. So let's talk about calculating and solving the phase diagram. So this is going to be one of those steps where you'll either really like it because you like solving puzzles, or you're like, crap, just tell me what to do and the steps there. So I'm going to show these steps, but these are just the baseline method to solve some of these phase diagram puzzles and to find all of these terms. But there's different ways to get to it, so it's kind of like a puzzle, thinking about what is given to you, what you need, and what equations or what density relationships you can use to get in between those two. So obviously the first thing you do with any problem is you list the information you know. So this will be in the problem narrative, or it'll be based off of your lab testing available. In the real world setting, it'll be what can your lab actually do? Can they calculate or can they measure density? Do they have the ability to actually measure void ratio or not? Obviously, we know measuring moisture content's pretty easy, right? Because all you need is a scale and an oven and 24 hours. So that's usually one that is given to you. So what are the variables that you know? The next thing that I always like to do, despite following the equations, is always draw the phase diagram. You don't need to draw it all perfect, pretty. You can just list kind of category right next to each other. But I think that really helps illustrate or help you fill in the blank a little bit. And it helps you not make a mistake. Because if you can physically see that, okay, this arrow for volume of voids, or sorry, the arrow for volume of water is less than the volume of voids. If you calculate a value that a volume of water greater than volume of voids, then there's an error there, So I always think drawing it out is a helpful tool. Next, then, think of the physical meaning and relation between each of the knowns and the unknowns. So don't just think of them as the numbers, but think about what that number actually represents when it comes to this phase diagram, or the soil sample that you're given. The thing here that always trips people up is if there is no total mass or total volume given, then it is okay to assume a unit value of either 1 cubic meter or 1 kilogram, but that is only if nothing is given to you. And the reason why we can do that is because all of these ratios that we care about are all ratios. They're all values divided by themselves are all unitless. So if you're assuming a unit value, that ratio is still going to be the same whether you have that actual thing or not. So the whole purpose is just solving it. So once you fill in one side of the diagram, it's kind of like a Sudoku. Once you fill in one thing, then you're able to solve for something else, because you can use density to transfer between the weight and the solid portion. So maybe you're given density, or at the very least, you can at least run a test and do the specific gravity, and then do that for the weight of the solid and the volume of the solid portion, so you can always kind of fill in the blank either way. So I always think it's really helpful to write out the equations in symbol form. So like volume of void over volume of solid, and then place the numerical value along with its units in the same order. And always following the units is important, because sometimes you might be getting data at different times, so like maybe the lab tech changed and they accidentally put the units in like cubic centimeters instead of cubic meters, or so on and so forth. So always writing your units down helps you keep track of everything, because at the end of the day, they have to be in the same units to be unitless when we divide them by each other. Okay, let's do a example here. So you're actually gonna have to do math and write stuff down and stuff. All right, so we have a soil sample. It has a water content of 18% and a natural unit weight, so bulk unit weight as is in the field, of 118.5 pounds per cubic foot. The specific gravity of the solid was found in the lab to be 2.72, so a little bit more dense than quartz. What is the dry unit weight, the void ratio, and the degree of saturation of soil in this state? So I'm already write out the given thing here. Something else that is very helpful and I would recommend doing is right off the bat, before you put anything else there, look at the units, like highlight the units, and then think about the unit weight of water that you're going to be using. So in this case, write it down so you don't mess it up. Every year, I see this using the wrong value here for unit weight of water, and that will screw up everything. Also, again, on the FE, which you guys are hopefully going to be studying for soon, the FE is multiple choice. Guarantee there's going to be one of those correct answers or false red flag answers, multiple choice, where you would find this value with the unit weight of 10 or 9.81 kilonewtons instead. They know this is an easy area. So always just defining it, writing it down. If you write it down, hopefully that'll help your brain remember that as you're solving it. Okay, so let's draw our little 3 rectangles here. You'll notice it's all blank stuff inside. And so what we need to do is first fill in the information that we're given here. So what we know, the first thing that we're given is the density here. And so let me just put it on one side or the other. So let's say the mass is going to be on this side, or I should say weight. Just pretend that says weight. It's going to be in pounds. And then the volume is on this side, which is going to be cubic feet. So we're given the unit, the density, 118.5 pounds per cubic foot. We're given the moisture content, and we're given specific gravity. Let's think about what each one of these things represent here. So we know that the density is our weight of our solid plus our weight of our water divided by the total volume. We know that the moisture content is the weight of the water divided by the weight of the solid portion. We know that the specific gravity, and I'm just going to shoot it out here a bit, is equal to the density of our solid portion divided by our density of water. So that's what we know for now. And what can we start filling in, or what would be the first thing we could fill in here?
Weight of the water.
The weight of the water and the
On the outside, you can put like 18.5 for the math. Like 1.
Yes, that's the first thing. So since we're not given a volume or a mass, but we are given the density, what we can do is assume 1 cubic foot of materials that we're using. Because essentially that's what this density is telling us, right? We have 118 pounds divided by 1 cubic foot. That's what density is saying. So for the volume, the first thing that we would do, we're going to use a unit value of 1 cubic foot for our volume. And once we do that, we can fill in the other side of the mass of 118.5. Sorry, that's an 8 right there. And remember, the mass of the air up here is 0. So what this equals is 118.5 pounds divided by 1 cubic foot. It's essentially what unit value or unit weight is telling us. So we are also given the moisture content, which is kind of nice, 18%. The moisture content is the ratio of the mass of the unknown over there. So with this, so we can rearrange this equation a bit to solve for one or the other. Let's just say we know the weight of our water is going to be equal to 0.18 times the weight of the solid. Now, how did I get 0.18? Yeah, because now we're in math mode, so we take away the decimal and we're like, we're business now. We're not expressing it in percentage. We're going back to the numbers. So we're gonna put that in through that there. So now we have the weight of water as a function of the weight of solid. And so we need to fill these two things. We need to find the weight of the water and the weight of solid, which are two unknowns. But do we have two equations that we can put together to help us solve for this? So not the total weight, but let's just say this. Sorry, I just naturally, well, unfortunately use Gator colors here. But we know that this right here, weight of solid plus the weight of water is equal to 118 pounds, because that's also what shows right here. So if we plug this in right here, what we get is, hope green works, but we get only one equation with one unknown, which helps us a lot. So what we get is weight of solid. Does that turn out okay? Yeah. I'm gonna go to black. So weight of solid plus 0.18 times the weight of solid is equal to 118.5 pounds. So this is nice. We can just solve for this. This is 1.18 weight of solid is equal to 118.5 pounds.
You just leave out volume flow to be equal to 1 here. Because shouldn't it be WS plus 0.18 WS over ET?
Yeah, it could be, but anything divided by 1 is, yeah. Yeah, but what I'm like, this equation in orange right here that I tried to box, that's essentially this on the mass side. As you see this 118.5, this is equal to these two added together. So yes, the 1 is in there because of volume, but we transfer that over and now it's only on the mass side. So what we can do now is we can solve for the weight of the solid portion. The weight of the solid is 100.4 pounds. And then we can plug that weight of solid back into our weight of water equation. Or we can just think about it this way. Weight of solid is 100.4. So there's two ways we could solve that. We could either go based off of 118 minus 100.4 or plug it back into it. But at the end of the day, we get the weight of water to be equal to 118.1 pound, or 18.1, I'm sorry. So then we do our checks in our mind right here, and we see, okay, the total weight is 118.5. We have these two things that add up to 118.5. You see, so like if the weight of solid was greater than 118.5, then something went wrong. If the weight of water was greater than 118.5, then something went wrong. Okay, so we have our mass side filled out already, which is really nice. How do we get over to the left side now? So we have our mass. How do we find our volume? Yeah, the triangle. We draw a little triangle. Mass is equal to, well, yeah, I mean, it's equal to the weight is equal to the density times the volume. So this is where these guys come in handy, our weight of water and our specific gravity of solid. So we know that our density is mass, or weight divided by volume. The weight of water, density of water is 62.5 pounds per cubic foot. What is our density of the solid portion? I don't know. Oh, remember specific gravity? What is specific gravity equal? Density of solid divided by the density of water. So if we want to find density of solid, we just take this guy and we multiply it by 2.72. So that'll be whatever that number is. I think I've written down. Let me see. 169.7 pounds per cubic foot. So remember, we have the weights of both of these, and we know the density already of water. So I'll just put this here. And now we know the density of our solid portion. Yes, mass is the same as weight here. Yeah. Yeah, sorry. That's what I'd said earlier when I wrote this. This should technically be weight. Oh. Okay, so let's just do this math really quickly and then we can get out of here. But our volume of water can be calculated again by rearranging this. So volume of water is going to be the weight of the water divided by the density of the water. Now our weight of our water is 18.1 pounds and our density of water is 62.4 pounds per cubic foot. So I'm just going to put that here just because we're running out of time, but 18.1 pounds divided by 62.4 pounds per cubic foot. And so what we're left with is cubic feet. So we have 0.29 cubic feet. That's a 3 at the end, cubic feet at the end. So let's go ahead and just plug this in here. So this is 0.29. Boom, we found that section. Now let's do the same for our volume of our solid portion. So is our weight of our solid divided by our unit weight of the solid. So that is 100.4 pounds divided by what we just found, 169.7 pounds per cubic foot. And the volume of that is 0.59 cubic feet. .59. And we do our little checks. We know the total volume that we assigned is 1. So both of these values are less than 1, right? So at least that looks good. Now, when we add them up, should they equal 1? No, they should not, because we have a little arrow here that still needs to be filled in. Because we have an air. The air has volume, but it does not have mass. So this is helpful though, because now we can find the volume of air easily, because we know the total volume, and we can subtract out the volume of water and then subtract out the volume of solid. And that will get us our volume of air. So the total volume is 1. We subtract out 0.29, and then we subtract out 0.59. And our volume of air, what is that math? I didn't write it down. Oh God, what was it? 0.12. This is cubic feet here. Okay, so now that we have everything filled in, finding these is super easy. It's just plugging it all in, right? So our dry unit weight is the weight of the solid divided by the total. Our void ratio is the volume of voids, which we didn't technically calculate, but it's these two added here, 0.12 divided by 0.29. And then degree of saturation, likewise, are those easy values there. So just, I mean, hopefully that's clear. On the next page, I'm just going to show you those calculations really quickly. Just to help, because you'll need that, like, just so you can follow it through. So yeah, we know the weight of the solid over the volume total. So this is 100.4 and our total volume is 1. So this is 100.4 pounds per cubic foot. Our void ratio, which is E, this is our volume of voids divided by the volume of solid. It's 0.41 divided by 0.59, 0.7. And then our degree of saturation is volume of water divided by the volume of voids, which is, what was the volume of water? 0.29 divided by 0.41. Then we multiply this by 100, and it will be 70.7%. I think. Okay, so we obviously didn't finish the next example. We'll start off next week on that, but still your quiz is, we'll have questions based off of this and on Tuesday's lecture. So you should still be able to complete the quiz that's posted on there. So follow through these steps and we'll go over some more examples. If you want to try to cover these examples ahead of time, then you can, but we'll have more examples and this will be something we'll be working on the next couple weeks. All right, enjoy your weekend, guys. See you later. Yeah, awesome.